Welcome to today's masterclass, everyone. I am your host, and आज हम लोग कुछ बिल्कुल mind-blowing unpack करने वाले हैं. We're looking at the ultimate proof that light is not a longitudinal wave, but a transverse wave. Yes, today's explainer is all about light polarization. So grab your notebooks, get hyper-focused, Kiki, we are going deep to make sure each and every concept is literally at your fingertips by the end of this. Let's get started.
तो ये रहा आज का syllabus. We've got 6 core sections to cover today. 1. Basics of light polarization. 2. Types of polarized light. 3. Methods to polarize light. 4. Key polarizing laws. 5. Double refraction and retardation. And finally, 6. Real-world applications.
Okay, let's dive right into this. Section 1. Basics of light polarization. Before we can manipulate light, we gotta understand the foundational geometry of light waves. Now, dhyan se sunna. I want you to memorize the exact difference between two key planes. First, we have the plane of polarization. This is the plane where there's absolutely zero vibration of the electric field vector. None. And perpendicular to that, we have the plane of vibration, which actually contains all those electric vector vibrations. Keep this distinction crystal clear in your mind, okay? It's a crucial fundamental concept that everything else builds upon.
To really visualize this, break the fourth wall with me for a second. Imagine you're holding a rope that passes straight through a wooden fence. If you send unpolarized vibrations, waving the rope around in all random directions, through a vertical grate, only the vertical vibrations are going to pass through. The horizontal movements get completely blocked. And guys, that is exactly what a polarizer does to unpolarized light. It acts just like that wooden grate, filtering out all vibrations except the ones aligned with its specific transmission axis. Samjhe? Great.
Moving on to Section 2. Types of polarized light. Let's see how this builds up when light passes through different mediums. Ab dhyan se sunna, because things are about to get a little mathematical here. When light gets polarized, it essentially falls into 3 main categories. We've got linear polarization, circular polarization, and elliptical polarization. Let's look at exactly what causes each one. Let's break this down like we're standing at a blackboard together. The state of polarization ultimately comes down to 2 orthogonal plane waves combining. The final type of polarization depends entirely on their phase difference, which we call delta, and their amplitudes. For linear polarization, that phase difference delta is exactly 0 or pi. But if delta is pi over 2, meaning a 90-degree phase shift, and the amplitudes are exactly the same, boom, you get circular polarization. Now, what if that phase difference is still pi over 2, but the amplitudes are different? That is when the light wave rotates as elliptical polarization. Make sure you memorize how this delta dictates the shape. Section 3. Methods to polarize light. All right, now that we know what polarized light is and the physical forms it takes, we need to know exactly how to create it in the real world. Scientists and engineers basically rely on 4 step-by-step methods to force unpolarized light into a polarized state. Step 1 is reflection. Step 2 is selective absorption, which we also call dichroism. Step 3 is double refraction, or bifringence. And step 4 is scattering. And this brilliantly illustrates that second method, dichroism. You see, certain materials strongly absorb one of the 2 plane polarized components of light, while letting the other pass perfectly through. To create the modern Polaroid sheets we use every single day, manufacturers take microcrystals of a dichroic material, like an organic compound called herapyth. They align their optic axes in one single direction, join them using a fast-drying nitrocellulose, and sandwich the whole shebang between glass. You've essentially just built a microscopic version of our wooden grate. Time for Section 4, Key Polarization Laws. We're shifting gears to the mathematical rules governing these phenomena. And listen, students, these formulas are absolutely essential for your exams and for real-world engineering. First up is the law of Mullis. I equals I naught times cosine squared theta. What this brilliantly tells us is that when completely plane polarized light passes through an analyzer, the intensity of the transmitted light, that's I, varies directly with the square of the cosine of the angle theta between the transmission axes of the polarizer and the analyzer. If that angle theta hits exactly 90 degrees, cosine becomes 0 and literally no light passes at all. Next up, we have Brewster's law. When unpolarized light hits a surface, both reflection and refraction happen, right? But Brewster discovered something amazing. At a very specific angle of incidence, the reflected ray becomes perfectly linearly polarized. At this exact angle, the reflected and refracted rays are perfectly 90 degrees to each other. This geometry is an absolute game changer for controlling optical reflections. Section 5. Double refraction and retardation.
Let's push our understanding even further and jump into the complex but super fascinating world of birefringent crystals. When light enters these special crystals, it undergoes double refraction. It basically splits into an ordinary ray that follows normal laws of refraction and an extraordinary ray that completely ignores them. We contrast these crystals into two distinct types. Positive crystals, and examples you must have on your fingertips, are quartz, ice, and rutile. Then we have negative crystals, like calcite and tourmaline. The main difference? It just lies in how the velocity of the extraordinary ray compares to the ordinary ray inside that specific medium. Now, what's really interesting about this slide is how the math we discussed earlier maps out visually. These distinct polarization shapes directly map back to that phase difference, delta, between the ordinary and extraordinary rays. Look here. When delta is 0, you see a straight diagonal line representing linear polarization. But as delta shifts to pi/2, the shape opens right up into an ellipse, or a perfect circle. The underlying equations literally dictate the physical shape the light wave takes. So the crucial point is how we engineer this to our advantage. Enter the quarter wavelength retardation plate. By cutting a crystal to a highly precise thickness, we deliberately introduce a phase difference of exactly pi/2, a 90-degree phase shift. If you send linearly polarized light into this plate at a 45-degree angle, it elegantly transforms that linear light right into a circularly polarized output. This is exactly how we manufacture specific states of light. Finally, Section 6, Real-World Applications. All right, I know that was a ton of heavy physics, but I promise to show you exactly why all these equations actually matter in your everyday life. Take mountain photography, for example. Slapping a polarizing filter on your lens drastically darkens the sky and cranks up the color saturation. But how? Well, by filtering out the unpolarized scattered light up in the atmosphere. You block all that messy scattered light, and you're left with a crisp, incredibly vivid image. And here is Brewster's law working in reality. When sunlight reflects off water at certain angles, it becomes highly horizontally polarized, creating that really intense blinding glare. But by wearing polarized sunglasses equipped with a vertical transmission axis, you completely cut through that horizontal water reflection. It's literally physics on your face. And it's not just for pretty photos or nice sunglasses. When a simple plastic knife is placed between two polarizers, the light suddenly reveals these brightly colored, totally invisible structural stresses hidden inside the material. Engineers use this exact polarization technique to visually test structural vulnerabilities in plastics, complex models, and even aircraft window panes just to ensure our safety. Which brings us to a final, provocative question for you all. We know certain substances, like sugar solutions, have optical activity. They naturally rotate the plane of polarized light clockwise or counterclockwise. So, if optical activity rotates light based on the length and concentration of a substance, how could this exact phenomenon completely change the way we test food purity? Think about it. By using an instrument called an optical polarimeter, we can instantly test the precise sugar concentration in a giant food factory, literally just by shining a polarized light through it. I really hope this masterclass leaves you eager to go out and research optical polarimeters next. Thank you so much for attending today's explainer. Class is dismissed. Keep learning.